All right. Hello, everyone. My name is Hyrum Chen, and I will be reviewing Lecture 10, Periodic Trends for Chem 105. So to begin, we have here the periodic table, which we will be looking at for the lecture review today. The periodic table obviously contains a lot of information with each element, atom, uh, the number of protons, where you can also find the atomic mass and the number of electrons from the periodic table. There's a bit more to how it's organized, which we're going to dive into today, and other things like that. So to begin, we're going to look for trends with metals, metalloids, and nonmetals, which are the extended family. The Z effective charge, the atom and ion size, and how that changes across the table, ionization energy, what that is, what it means, and so on, and then electron affinity. And so a quick review with using the table is the first thing is we have groups and periods. Let me go back to the table. So groups here are columns that go down vertically, and then the periods are what goes across horizontally. So they have each of them numbered, so then when someone asks or labels something by group 15, for example, we can look on group 15 out of all of these. And the groups are laid out in such a way that they have the same electron, or excuse me, the composition is similar by the groups. And you can see how they react similarly with chemical reactivities. Then the rows, or the periods rather, are like the same energy shell. For example, we have like the 2s, and then it'll go into like the 2p here, which is something to keep in mind as we go into the uh, electron size and so on. And so the last part is that there are different types of metals in the families by the groups. And so here, as you can see on this here, we have the alkaline metals on group 1, the alkaline earth metals on group 2. This big chunk here is like the transition metals. And then we have group 13, group 14, group 15. They don't have any specific names. And group 16 also. No specific names for these ones. For the groups, but we also have by the color here, as you can see, there's like the metalloids, and then the green here is like the non-metals, and then 18 is the noble gases. And so those are like the main families we have, and then we'll get into the extended families now. So while they have these specific families, there's a larger extended family of just the metals, which is quite all inclusive. For the colored ones here, the ones that are white are not included. So metals are great conductors. They tend to be shiny and malleable. And then we have the nonmetals. The nonmetals are right here, the green and purple. And so the nonmetals are liquid and gas at room temperature. And they are non-conductors, so not very good at conducting electricity or heat. Next one we have is the metalloids, and so metalloids are kind of the in-between of metals and nonmetals, and they're shiny like metals, but then brittle like nonmetals. Some of them are good at conducting electricity and heat as well. And so now that we've talked about the families of the periodic table, we can jump into the trends. We're going to start with atom size, and then after we talk about atom size and how that trends on the table, we'll go into ion size, and then after that, ionization energy, and lastly, electron affinity. So the first one is atomic size. Atomic size is determined by the distance between two atoms' nuclei. In the elemental compounds, it is the distance between two nuclei. So if you look here at this image, we have Cl2, and then here are a combination of the Na atoms. And so looking at this in the image here, we see how there's an overlap on the Cl2 and then not an overlap at all in the sodium where they're just edge to edge. And so when we look for an atomic radius, it is simply the distance between the nuclei of two atoms divided by 2. If that makes sense. Because sometimes there's an overlap here. It's not edge to edge always. So that's why we just do half the distance between two nuclei of the same atom. And so atomic size decreases across the table. So as you go right down the row, it's going to decrease in size. We'll get into why later. And then atomic size increases as it goes down the table. So the further along group you get, the bigger the atom size. One thing to note is that transitional metals are a bit unique. This is to do, I believe, with the energy shell, the D shell. But essentially, the size does not vary too much across the transitional metals here. And that would be because they just don't do that. And so the next part is the ion size. So ions are split into two parts. We have cations, then we have anions. And so here is an image where we have both. A cation is an atom that loses an electron. And so as you lose an electron, you're essentially losing a negative, which makes them positive. That makes sense. So if we look at the potassium here, this one's going to be a cation. So potassium, as it becomes a cation, it loses an electron. So it becomes positive. And then an anion is just the opposite. So if you look at these ones here, for example, iodine, we have iodine, and as it gains an electron, an anion will gain an electron, it will become bigger, and it becomes more negative, so it has a negative charge. A simple, easy way to remember, I just have it written out here. Positives are cations, right? And they are smaller than the neutral atom, as we see here, which is smaller than an anion. So when we jump into in cation, so when an atom loses an electron, it becomes positive, which is a cation. If you think about the atomic size, your atom's charge is still the same. So the amount, which is related to the amount of protons you have, right? So the atom's charge you have is still the same, and it's pulling on the electrons, but you have less electrons to pull on when you are a cation because you gave one of your electrons away. And so the force per electron increases as you have less electrons to pull on. And therefore, the cations are smaller in atomic radius than the neutral atom because you have more force pulling on each electron as you have less electrons. I'll just try and repeat that. So your nucleus is applying a force on all of the electrons here. And so all your protons here are pulling in on your electrons. But when you give away one electron, that doesn't mean that your protons have decreased. And so you still have the same amount of force pulling, but you're pulling on less. So you think about it like if you're pulling a 15-pound weight with as much force as you can, and then all of a sudden you drop off 5 pounds and you're pulling a 10-pound weight now, you can pull that 10-pound weight with a lot easier than you can pull a 15-pound weight when you exert the same amount of force. And so you can pull a lot. You can pull the weight a lot better That makes sense. So when when you have a cation, the radius becomes smaller because the force pulling on those electrons per electron is a lot greater. Now with the anions are the opposite, the flip side. So again, an anion is when an atom gains an electron, making it more negative. And so when you gain an electron, the Z effective or the force per electron decreases per electron. The force itself doesn't actually decrease, if that makes sense. So the atomic radius then increases because it pulls more electrons with the same force, and so the radius is bigger. So going back to that analogy where you're pulling weight, if you're pulling weight with as much strength as you can, which is consistent, when you pull 10 pounds, you can pull the 10 pounds a lot easier than you could 15 pounds. And so when you add an extra thing to pull, so if you add just 5 pounds, the how much you can pull it is going to decrease because you have to the force applied per pound is less, if that makes sense. And so in this case, when we have the anions here, we have more electrons, and so the effective force, it has to pull on more, and so because there's more to pull on, but the force doesn't change, your electrons aren't pulled in as tight, and so that's also why, and you have more as well, so the size increases with an anion. So protons in an atom apply force via attraction. The amount of force applied is reduced or blocked by other inner electrons being in the way. The Z effective is an average overall of the force of attraction in an atom. Basically, total force minus blocked force is going to equal your Z effective. In other words, the Z effective is the force that is actively pulling. And then more protons means you have more electrons. And more protons also means more pulling inward force because of your charge is higher. And force is reduced when the distance is greater. So the larger the atom is, like the atomic radius, the Z effective is a bit lower. So that's why we see on the trend here. Let me go back to it. Oh, let's see. Right here, sorry. As the atomic radius increases going down, the Z effective is going to increase the opposite direction. And so now one thing to note is the shielding. It was mentioned briefly here with the blocking. And so since Z effective is basically what charge is felt or received by the electrons, it's important to note things that reduce or prevent the pulling force. Like I mentioned, the shielding and the distance. One way I think about the shielding is if you look at this image of the Wii Sports, fun game, right? So in this bowling alley, there are objects in the way, and then our goal here is to obviously knock down the pins. And so with the nuclei or the nucleus, when there's something in the way, it prevents us from applying force on what we actually want to apply force to. And so with the atoms, when there are other electrons in the way, like this obstacle, the outer electrons aren't able to receive that pulling force from the nucleus, and so that creates or reduces or prevents the Z effective on the outer electrons because the inner ones are blocking it. And then the next part is the distance, and it's just this equation here, Coulomb's law, which is your charge divided by the distance. And so as your distance is greater, your force will decrease. That makes sense. So in the same group, your number of protons increase. So that's your charge on the right here, as you can see. lithium has +3, and then fluorine has +9. And this is what pulls the electron into the center. So when you have more protons, your pull is greater when in the same shell. This is why when you go across periods, the radius decreases, but then increases as you go down another period, because when we go down another period, we add on another energy level or another subshell. And so one thing to note though is that looking at the charge only properly applies across periods, because like for example, when we look down like a column or a group, they'll all have the same positive charge, right? Um, but when we want to consider the charge, it only applies when we look across the periods, not down. So the next part is the ionization energy, and this is the energy required to remove electrons. It is easier to remove an electron from an atom that is bigger. If we think back to the Z effective, because if we're pulling off an atom, if it's not being pulled very well to the center, it's easy to take it off and take it away from the center because the center's not pulling as hard. So in as atomic radius is smaller, more energy is required. So opposite to the atomic size, again, atomic size increases as you go down and as you come across to the left from the right. So the opposite will be for ionization energy. So one thing to note though, atoms like beryllium and boron, and then magnesium and aluminum, because of their subshells, they go from 2s here to 2p. And so there's a small drop in ionization energy at these shells because of that. Another thing is ionization energy does not stop at removing just one electron. You can continue to remove more than one. And so as you do so, the amount of energy required to remove it is gonna increase. And if we think back again to the Z effective, same idea, that as you have less electrons, the force per electron is greater. And so if you're removing more and more electrons, you have to pull even harder to break that, to overwhelm the force that the Z effective applies. Another thing to note is that ionization energy is always going to be a positive value because it's a measurement of energy in joules, kilojoules. Next up is the electron affinity. And so the electron, this is the energy change when adding an electron to an atom. And the energy can be positive or negative depending on if the atom is seeking to gain an electron or not. And so if it's negative, that means it is seeking to gain an electron. If it is positive, it is seeking to discard or repel an electron. Halogens are the most common as they seek to gain an additional electron to fulfill the octet rule. So they're going to be like they're going to have the greatest negative value. On some exceptions though, some groups on here do not have high electron affinity because this is going to be because of the filled subshells. And so like if you think back to the 2s shell, here they have fulfilled they filled their subshell, they paired off, and so they don't have the need to seek another electron. And that's the same case with the half-filled as well, to a smaller degree. As we see here, like nitrogen has a value of 0. And then, of course, with the halogens, or excuse me, not the halogens, the noble gases here on group 18, they're all 0 because they have fulfilled the octet rule, and they do not seek to gain another electron. If that makes sense. Another thing is that the most positive or the closer it is to 0, the least electron affinity there is. And so the more negative means the more they seek it, right? So if we look at the halogens in group 17, they are very negative in comparison to the noble gases, and so they seek to they seek to gain an electron more, hence their value being greater. And so that was a review. Just to do a small recap, I'll go through again briefly through all the slides. Again, the periodic table here. And then we have the families, different families, metals, nonmetals, metalloids with their respective qualities. And then we have atomic size increasing to the bottom left of the table. And then we have the ion size, which is when a neutral atom gains or loses an electron, becoming a cation if it loses an electron, and becoming an anion if it gains an extra electron. And Z effective is the force pulled by the nucleus on force applied onto the electrons, which can be influenced by the amount of electrons, and it can be influenced by the shielding and the distance from the electrons. Then we have the ionization energy, the energy required to remove an electron. And then lastly, electron affinity, the energy change when adding an electron. So I hope this helped. Good luck for all your studying as well. And yeah.